And we're taking calcium ion, bicarb molarity, ammonium molarity would be the same. And the equilibrium molarity of ammonium ion simply to be 1.0, the initial molarity, less S. Right? Because whatever is the ammonium molarity, it's got to cooperate with this relationship. It's got to keep with this relationship. Because in this pot, if ammonium ion loses H+, you got ammonia. That's it. Vice versa, if ammonia gains H+, you got ammonium ion. There's no other forms of nitrogen-containing things in this pot. So, with this before us, the arithmetic is really simple. That gives this. And now, we will ask the $64 question. Is this result accurate? If you were in the laboratory, what would you do to find out if this result is accurate? Or let me say it this way. Can this be tested by pH measurement? Because we got pH meters for you to use in the laboratory. Can the arithmetic we have so far done have its validity tested by pH measurement? Is that possible? What do you think? Damn right it's possible. So if I set you free to pursue this in the laboratory, you would take what we have done so far, and on the basis of what we have done so far, calculate the hydronium ion molarity for the system from which you could get pH. We're going to do that in a minute. And then you go to the laboratory, and from the side shelf get some 1.0 molar ammonium chloride solution. And do what with it? Holler for your TA? Run to the stock window? Go knock on Horvath's office? What would you do now? Would you also go to the side shelf and get some calcium carbonate? Stir it into the 1 molar ammonium chloride solution until you produce this system? Saturated calcium carbonate in 1 molar ammonium chloride solution. And then go to your pH meter after it's tuned up and measure pH. Because if the measured pH and the calculated pH are the same, you got a winner. That makes this right. Okay? Well, let's take on the calculation of hydronium ion molarity based on this. So I'll write to test what we have here done. Calc this based on above. Okay? How would you like to do that? Any suggestions? From what we have so far done, can we calculate a pH? You betcha. Well, how are we going to do it? Tell me what to do, and I will gladly write it on the board. Well, I'll provide another hint. Example. That's what we want. And from what we have so far done, we got a value for this? What is it? I don't think so. There it is, right? Isn't S the same as, based on what we've done? S is the calcium ion molarity, it's also the bicarb molarity, it's also the ammonia molarity. Okay. So this is 4.2 times 10 to the minus 3. What's this? How many unknowns we got now? 1. And so now we'll do the arithmetic. .3 times 10 to the minus 7, for which pH is 6.89. Now, we don't have here with us a pH meter. We don't have here with us 1.0 molar ammonium chloride solution. Got calcium carbonate. But because of the absence of the pH meter, and the 1.0 molar ammonium chloride solution, because we're not in lab really, I cannot pursue testing the validity of what we have so far done by experimental measurement. But there is another way. What's the other way? How can we approach this problem so long as we don't make any arithmetic mistakes, to be sure we get the correct hydronium ion concentration? Because right now we've got this, but we don't know if it's correct. We think it's correct, or we suppose it can be correct. What can we do right now to see if this is correct? What can we do? Holler for help is not an acceptable option. Writing a written appeal to President Machen is something you can do, but I got a feeling that won't get the answer, because I've not yet seen him as a member of my class. And if you haven't been a member of my class, my bet is you don't know how to do this. But you should know how to do it, because we've already given you the tools. So what I'm appealing you to do is to use the tools with which you have been armed. What are the tools? What are the tools? Did we not say at the end of chapter 18 that you can, with what we gave you in chapter 18, calculate correctly the molarity of any and all species which live in water solution and who have a lifetime that depends on pH. Did we say that? Well, what did that depend on? It depended on equilibrium analysis supported by what? Did you hear what I said? Did you hear it that time? Material balance and charge balance. Did you hear it that time? How about that? So let's do it. Now for reference, for rigorous test. See? BQ2. I used to call them bonus quizzes, but I changed their name to special quizzes. 46, summer 11. If you look at the key to BQ2 46 summer 11, I have a copy of it here in my hand. You'll see how we play the game. Let's take a look at the nuts and bolts of this. We got the equilibrium reaction and the equilibrium constant expression over there. So I don't want to write that again. The material balance equations are this, which we've already noted, and what else? What's the other stuff in this system with which we are concerned? Carbonate-containing things? So, to do this puzzle part, what are we going to do? Uh-oh. Must be an important message. I swear I see students walking down the street, standing next to each other, but not talking to each other. This way. They're talking to the cell phone. Don't you think it's strange and unusual that the world managed to get this far without cell phones up until a few years ago? Gee, how could they possibly have survived? I don't know. How could they have survived? How could they have survived without television? When I was born and raised, no TV. You know, back in the Stone Age. Now then, what's the other part of this puzzle? Charge balance. So, right now, just because you need the practice, okay? There's our system. On your paper right now, write down the complete correct charge balance equation for this system. And see if you can set it equal to a charge sum. Have you recognized that in writing these charge balance equations, all you're really doing is taking advantage of your knowledge of PSI? And now supporting it to the extent of writing a complete species charge balance? Because some of the molarities with which we are concerned for this system are going to be tiny. We've already recognized that by the small k value. So for this, we want to write a complete species charge balance relationship. Did I leave anything out? Chloride ion. I left out chloride ion, didn't I? But I'm not going to write down chloride ion. Instead of chloride ion, I'm going to write something else down. What should I write down? Instead of writing brackets surrounding chloride ion, I'm going to write something else down. What should I write down? I'm listening. I'll give you a hint. I'm going to write down a number. What is this number? 1.0, right? And why is this number valid? Is that not the molarity of chloride ion in this system? Is chloride ion a participant in any chemistry we are here considering? So the chloride ion goes in the solution when we prepare this system and sits there as the proverbial spectator and watches all this fun chemistry take place. But it's there, and its presence is recognized in the charge balance equation. And now, by a series of appropriate substitutions, we can get S, which we want to get, which is equal to the calcium ion molarity, equal to hydronium ion molarity squared times 6.15 times 10 to the 8th. Oh my golly. Plus hydronium ion times 1.3 times 10 squared divided by Kw over hydronium ion. What do you think this corresponds to? What's this? Hydroxide ion molarity. Plus 5.6 times 10 to the minus 10, which I hope you recognize as Ka ammonium ion, over hydronium ion, plus 5.6 times 10 to the minus 10. Gee, what a horrid expression. Absolutely horrid. You can look at the reference to see how this has been obtained. For your own benefit, sit down with pencil and paper and do it. It's not difficult at all. The part of the puzzle which will frighten you is the fact that rather than X's and Y's and Z's, this thing contains formulas for chemical species. So, we're going to now write another statement. Use above, that's this horrible looking thing. And speculate on a value for the hydronium ion molarity. To calculate this. Now, when you do this, or if you do it, because if you want to learn from it, you'll have to do it. Would I ask you this on an exam? Oh, absolutely. And I can give you all night, and you can scribble and scratch and a ream of scratch paper and have at it and have fun, right? Okay. After speculating on this, on a value for this, you calculate this from this, and along with this, you'll be getting values for equilibrium molarity of ammonia, bicarb ion, and ammonium ion. So you'll be able to put all those into this. Okay? When will you know that you have the right value for the hydronium ion concentration? Based on this speculation. Because again, you're going to speculate on a hydronium ion concentration, from which you will calculate a value for the calcium ion concentration. And with this, if you do the arithmetic, you'll see it, it's not hard. You'll also get values for the equilibrium molarity of ammonia, ammonium ion, and bicarb ion. Correct values, so long as you don't mess up the arithmetic. When will you know when you have the right hydronium ion concentration? When will you know? When will you know? You will know when the values you get for the calcium ion molarity, put that in here. The bicarb molarity, put that in here. The ammonia molarity, put that in here. The ammonium ion molarity, put that in here. And get this number. That's when you know you got it right. Because we have now paid attention to equilibria, obviously pertinent to the system. and every possible component of the system with which we are concerned. Now, if you were now to pursue this matter, you would speculate on a hydronium ion molarity. Give me an idea what hydronium ion molarity might you like to speculate on first? Hint that follows from what we have so far done. Because if you've appreciated what we did over here, even though this might not be exactly on the nose, it's got to be close. We told you the reasons why this has got at least to be close. So to proceed with this arithmetic and calculate for this system the correct hydronium ion molarity, what hydronium ion molarity would you speculate on first? Another hint, to keep the arithmetic as simple as possible, I suggest you make a speculation, initial speculation on the hydronium ion molarity, which is numerically simple, but which you know to be, if not correct, close to what is correct.
1.06 to the next 10?
Absolutely. Did we not show that the pH of this system is at least close to 7? And the 2 sig figs, the hydronium ion molarity is 1.0 times 10 to the minus 7. Okay? That's the way to play the game. And it's not hard. But to learn to play the game correctly, you have to play the game. So let's write down a couple more things. You can check on this. References there. You do the arithmetic with this hydronium ion molarity speculation, which follows from what we've done so far. You'll get a calcium ion molarity from this of 3.4 times 10 to the minus 3. And for this, when you put in the corresponding values for bicarb molarity and ammonia molarity and ammonium ion molarity, you'll get 5.3 times 10 to the minus 8. That's pretty close to that, don't you think? Pretty close to 7.2 times 10 to the minus 8. So we know we're on the right track, but we're a little bit small. This number is a little bit smaller than this number. So how should you now adjust your next hydronium ion molarity speculation? Might you take further advantage of what we have so far done? Can you recognize that with this value being lower than this value, and this corresponding to a pH of 7.00, right? The true pH must compare how to 7.00 if, for that expression, we got a number smaller than 7.2 times 10 to the minus 8. The true pH must be a little bit, yeah. Try it. I get We'll pick it up from this point tomorrow.